Hello and welcome back to the first season of the podcast For Code in Research, the companion podcast for the course on research programming in C++ from the Advanced Research Computing Centre at the University College in London. It's hard to believe, but we're already halfway through the course. And if you're a student at UCL, you'd be looking forward to a reading week. Well, it's nice to slow down a bit every now and then, isn't it? Alas, not so much for this podcast, where together with my guest Klaus Iglberger, I'm busy going through construction and design in this episode. Well, construction and design with classes to be precise. C++ gives you quite a few tools to help you design great software, and some of it, like inheritance, Klaus and I already went through in the previous episode on polymorphism. There is, of course, more building blocks and techniques. But also, once you have all the building blocks together, what do you actually do with them? In short, there's a lot to cover again, so let's get started. As I said in the first introduction episode, Björn Strostrup got his inspiration of what he called C with classes, which of course turned into C++, from a language called Simula. But when it comes to creating and implementing a class in C++, the way the code looks is almost identical to a type that evolved from the C programming language, and it's called a structure, or simply called struct in C++ and C. Structs were introduced in C to allow grouping together of variables of different types and roll them into a new custom type. C++ built on the idea, but it developed it further. In C++, structs are in fact equivalent to classes, where all members are by default public, whereas in classes, members are by default private. And when I say members, I mean not only variables, but also member functions. On top of that, structs, like classes, can have constructors and access specifiers, and you can express inheritance in structs just the way you can do that with classes. But maybe I'm getting a bit ahead of myself. What do I actually mean by private? And what do I mean by public? To look at that, let's create a simple struct in C++. And let's call it person. It has two variables, one a string, which is called name, and the other an integer, which is called birth year. You can, of course, pack a lot more into the struct person, but let's start with that. The struct person I just created is, at this stage, little more than a compound type consisting of two variables of different types. Created as a struct with two variables that are declared simply as string or integer, every piece that has access to the definition of person can use the struct and read and change the value of the name and birth year variables. This kind of universal and unrestricted access to anything defined within the struct is something we call public. Public is an actual keyword in C++. And because it has something to do with accessing members of structs and classes, it falls into the category of access qualifiers. Well, so far we haven't really done anything particularly exciting, have we? So let's make this a little bit more interesting. Let's say I want to add another variable. Say, a variable called employee number, which could be a string or an integer. The type really doesn't matter that much, because what matters to me more is the fact that I don't necessarily want to share the employee number with every single piece of code that is using the person struct. Luckily, in addition to public, C++ has another access qualifier called private. Private is something that is only accessible by the struct or indeed the class itself. So you could define member functions and variables that can access the private member within the struct or class, but not from anywhere else. So back to our struct person. We could define the employee ID as private, and that way no one but the struct itself can get or modify the value. Okay, that's one way of doing it, But then perhaps you remember that at the beginning I said that structs are classes where all members are by default public, and that in classes all members are by default private. So maybe we can turn all of this on its head, and instead of using a struct for person, we can use a class instead. But unlike in the struct, we have to use the public access qualifier for the variable name and birth year to make them available to outside the class. And because all members are by default private, we don't have to specify the access for the employee ID variable at all, because it already is private. How you manage access to member functions and variables is an important part of when it comes to designing software, as I'm trying to show next. For we're not really done with access qualifiers. Let's say that I want to create another class that inherits from person. Let's call this class researcher. And it has some variables too, like the name of the institution where the researcher works and an ORCID ID or a publication ID. Since the class derives from person, I expect that the class researcher has access to its member functions and variables. But has it? Well, for the name and birth year variable, that's true, but then they are declared as public and pretty much anything can access them anyway. But for the variable employee ID, we have a problem. It is by default defined as private, and therefore only accessible by the base class, that is, the class person. But C++ has got you covered. For in addition to public and private, we have a third access qualifier called protected. Using protected for functions and variables makes them accessible for the base and their derived classes, so we can now declare the employee ID in person as protected. And we can of course leave it like that, but it does feel a little bit odd, doesn't it? We have two public variables called name and birth year, and one protected called employee ID. So how about this? We declare all three variables as protected, so all three are accessible to the researcher class and the person class. And because we want to make the name and birth year variables visible to other parts of the code, we use a trick. We define two functions. Let's call them getName and getBirthYear, and we make both of them public. And next we define a default constructor for both classes, for instance for the person class that takes name and birth year and employee ID as an argument, so that each time you want to create a new instance of the class, you have to provide these parameters, and they're being set. So now we have a situation where the variables themselves can only be manipulated by the base and derived classes, but you can see what the values are when you use public member functions that give you these values. And that is a technique that you will see widely used not only in C++ but in other languages that use object-oriented programming models, like for instance Java. Defining and controlling the access of variables and functions is an important technique, as I said, when designing classes and class hierarchies. Because effectively you're defining a contract between the class and anything outside the class, in which way the class and its members can be used. So why, you wonder, is that good? Because, amongst other reasons, it helps break down complex code into smaller chunks, where each chunk does one specific or a limited set of specific tasks. It's what's called separation of concerns, and it helps on many fronts, for instance being able to test and maintain the code or find problems, for instance, easier. And object-oriented programming is designed to help you with that. That is, grouping functionality and sometimes data together and controlling how this is accessed from other parts of the software with classes and class hierarchies. Object-oriented programming is a paradigm that's been around for a very long time, but it is not the only one. And here Klaus and I talk briefly about the other paradigms. Hi Klaus, and welcome to week 5. Goodness me, it's already week 5. You know, times is passing quickly, and we're going to talk about classes, and there's really so much to cover.
Yeah. So it's great to be back. And indeed, classes is a topic that we could talk for hours.
First of all, before we go into classes and class design and how you design them, because I think you've written a book about it, we can maybe talk about that a little while. But there are different paradigms of programming, right? So people might be familiar with the object-oriented design, which is, of course, where classes come in.
Yeah.
There is the functional programming, which I think has gone through a bit of a renaissance in recent years.
Indeed, it has, yeah.
And there are actually programming languages that specialize on that, I believe. And there's also something called structural programming.
Yes. So I think you just mentioned the three basic or most fundamental programming paradigms. Actually, the first to be invented was functional programming. But of course, at the time it was invented, there was not really programming yet. So there was a lot of theory behind this. So let's start with structured programming. Edgar Dijkstra, probably one of the first programmers, or perhaps the first programmer we had, eventually realized that if you write programs that jump wherever they want to, do whatever they want to, are very hard to prove correctly. Edgar Dijkstra was somebody who wanted to formally prove his code. This was not about testing indeed, but he wanted a mathematical proof that the program was correct. And you cannot prove something that is pretty much chaotic. And so he wrote a paper, probably after he has done a lot of experience with that, but he wrote a paper and argued that go-to statements are harmful. Yeah, go-to statements.
Indeed, I do remember them from my Fortran days, which I think still has, or at least Fortran 77 have go-tos.
Exactly. So what he argued was that there should be real structure to the programming, and you can pretty much build any kind of program by just sequence of operations, some selection, and iteration. And you can package this in functions and then perhaps the functions in classes, but it should be a structured way of doing things. And this is what structured programming pretty much is all about. And implicitly, everybody's using this today. You will hardly find any modern programming language that allows you to jump anywhere in memory. There's a structure behind all of this. And so structured programming restricts you in the way where you can go, how you execute your code. Then object-oriented programming, the function pointers. A function pointer pretty much allows you to call any function. And it's some kind of abstraction too. Last time we were talking about polymorphism. Function pointer is one of these little tools to achieve that as well. But in C, we realized or experienced that function pointers can be very tricky. You never know what's happening. You never know whether it has been correctly set, etc., etc. And so the function pointer is a little unstructured. In object-oriented programming, especially now in C++, we've replaced that by order again. Classes with virtual functions set these function pointers for you. Virtual function is nothing but a function pointer, probably managed by the class. And in doing that, it's way simpler to get all of this right. Way simpler. The pitfalls in C++, it's never perfect, but at least the management of function pointers is done well.
Okay, it's safer.
And so object-oriented programming kind of restricts you in a way you use indirection, managed function pointers. And now the last one, function programming. Function programming is about working on things that do not change. Immutable data. Now, what I describe is pretty much what we call pure functional programming. This is not necessarily what every programming language immediately implements, but data should not change.
So could I just interrupt there for a second? I think we need to clarify pure functions because I think it has a specific meaning, doesn't it?
Correct. This is something else. A pure function is a function that always produces the correct result given the same input. So it's a function that you can very deterministically test. You have a function that takes an int, returns an int, or let's actually give a real example. The square root function takes a double, returns a double, and if you pass the same double, you will get the same result.
Right.
And that is because the square root function doesn't depend on any state. And there's nothing that could change that the function would behave differently. That's a pure function. And a pure function programming language, pretty much the idea is that everything is built from these pure functions. And so you can very predictably build your program based on functions that just produce output. So why is this great? If indeed you would not have any mutable data, if no data would ever change, you would never have any problems with concurrency. Many threads, anything like that, there would be no data races. There would be no any kind of concurrency problem. And this is why function programming today experiences a renaissance. We've realized that the way we do programming is not necessarily the right way in a multi-threaded application. Yeah, many threads sharing the same data, reading and writing arbitrary times, you never have any guarantee.
It's like the go-to just in the multi-threaded world.
Exactly. Yeah. And so now function programming gives us a little control of just that aspect. And so if you now take everything together, every paradigm kind of takes some freedom away from us. I would even argue some opportunity to create chaos. Structured programming does not allow us to go anywhere at any point, but there needs to be a structured sequence of things. Object-oriented programming controls indirection, and function programming pretty much controls assignment, changing data. And so all of them together might actually give us programs that are hopefully bug-free. That is the optimistic word, but that contain less bugs.
And are more robust, basically.
Correct.
Are we then in a world where object-oriented programming gets bit by bit replaced by functional programming? Are people still using object-oriented programming, or is it on its way out?
Some people would probably claim that or hope that this is exactly what happens. I am less optimistic here. I believe you do need object-oriented programming. Honestly, not on the smallest pieces of our code. I think this is where function programming is just tremendously helpful. Yeah, really accessing that data, really working with data. Doing this in a more functional style is extremely helpful. But if you now go to the big codes again, millions and millions of lines of code, organizing this code, this is so much more convenient with object-oriented ideas. The dynamic polymorphism, the inheritance ideas, the idea that it can just, perhaps even at runtime, replace one implementation with another one. This is where object-oriented programming just shines. And so I think it's a matter of perspective. I'm strongly believe you need both, but probably it's a matter of scale. Perhaps the smaller things are best solved with functional ideas. On a big scale, object-oriented ideas work better.
Okay, functional and structural programming paradigms aside, let's go back to object-oriented programming. And access qualifiers play, as we already discovered, an important part when you design and build your classes. But then there is also the inheritance that we touched on previously when Klaus and I talked about polymorphism. The example of person and researcher class I mentioned a few minutes ago are good examples for cases where the derived class adds to the function and variables of the base class, but doesn't really change the behavior. But that's only partially helpful when it comes to defining a class hierarchy. In the previous example I mentioned an example where this model of simply extending functionality doesn't really work. Remember? We talked about shape with two derived classes called triangle and circle, and the fact that for both the way they are drawn and the size calculated are fundamentally different. In that example, we used a different trick in C++. We declare the functions draw and the size calculation as virtual. That is, when we define the method in the class, we use the keyword virtual before the definition of the function. Setting the virtual function equal to 0 turns it into a pure virtual function, and classes containing such functions are called abstract, meaning that you cannot use this function directly. Instead, you declare the actual implementation of a virtual function in one of the derived classes. So in our example, the functions area and draw would be virtual functions in the base class shape, but the actual code for them would be in the classes triangle and circle. And since both calculate these values differently anyway, that's pretty much what we want. If you're coming from another object-oriented language, this may all seem a little bit odd at first. So for instance, in Java, you actually do have a keyword called abstract, with which you can declare an entire class. So maybe the way abstract classes are handled in C++ takes a bit to get your head around. The other thing that might be difficult to appreciate at first is what it's actually good for. I mean, after all, if triangle and circle draw and calculate their shape and sizes differently, well, why on earth should they be subclassed to something called shape in the first place? Well, first of all, there actually is a similarity. Both of them have a size called area, and both of them can draw. So there's some kind of relationship, even if the concrete calculations and implementations differ. But secondly, remember polymorphism? And the fact that pointers to base classes are type compatible to the ones for the derived classes? Well, this introduces a great amount of flexibility in your code, because you can use this fact for having the actual pointer to the class you want resolved at runtime. One of the techniques that uses this is called dependency injection. And perhaps you remember that Klaus talked about it briefly in the previous episode. In essence, you can use the pointer of the base and possibly abstract class, but have it resolved at runtime into another concrete implementation of one of its derived classes. And that is great in situations when you don't want to, or even cannot specify in code and at compile time, the exact implementation to be used. Okay, so far Klaus and I talked about different programming paradigms and the kind of building blocks or techniques in which you can organize your code with classes and hierarchies. But how do you do that? Well, that depends on the problem you're trying to solve, of course. And it is what is generally known as design and software architecture, which takes me to the second part of my chat with Klaus. So I would like to move on to another rather huge and sheer endless subject, which is class design and design patterns. So you've written a book about it, haven't you?
I have, yes.
About class design. So in a nutshell, if you can,
words, yeah.
What is it about class design and how do you approach that?
So I want to be able to manage my dependencies in the code. I want to be able to separate concerns. I think that's also something we've mentioned before. But I do not want to reinvent the wheel again and again. And so design patterns essentially are proven ways to organize my dependencies, to organize my software. There are many design patterns available. Now, a great source to look this up is probably the original book, the classic work on that from 1994. So the book is called Design Patterns, Elements of Reusable Object-Oriented Software. It's by 4 authors, and because of that, we call this the Gang of 4 book. It's actually a book written in C++, although at that time there was no C++ standard. So this is a book that was written in pre-standard C++.
Yeah, but people should still recognize it as such. Yeah.
Indeed. That's an important point to make indeed. But this book contained 23 design patterns. Design patterns that are still used today in various forms. Patterns like strategy, visitor, decorator. One of the big advantages of these patterns is that by just saying visitor or strategy or decorator, people already know what I'm talking about. People have an idea which kind of structure I'm aiming for. So if I say strategy, people think about this dependency injection idea again. I configure something by passing a pointer to base into something else. Whereas if I say decorator, people know, okay, it's not about injecting, it's about wrapping something. I create something around some other existing thing. And so these patterns are to help developers recognize solutions quicker, to understand code quicker, but also to properly organize the code in a way that, because people understand this, is more maintainable, more robust with regard to changes, again, reliable.
I think one of the difficulties of the Gang of 4, or indeed any design pattern book, is that there's such a wealth of them. It's to recognize when to use one and which one.
Yeah.
Like the factory pattern or the builder pattern, which is the Gang of 4. When do I use the one? What is the difference? Does it even make sense in my case? At what stage should I consider implementing or looking up a design pattern?
Yeah, that's a difficult part indeed. And honestly, many of the patterns look very similar. The factory method design pattern and the strategy pattern, the one I mentioned before, from a code perspective, almost look alike. But I would use them indeed for different purposes in different situations. To some extent, it's a hen and egg problem. So I can just ignore patterns, but then I will come to a situation where I could use them. Then it would be great to know them. But if I first learn them, then I might not really come to a situation or into a situation where I truly need them. So my recommendation is know about the most commonly used, the most important patterns. And you will definitely come into a situation where they apply, where they help. And then you realize, okay, it makes sense. You have the solution in the back of your mind already. You can reasonably quickly implement this using the right terms, the right names. You can communicate your solution to others.
You're thinking about creating a class. the way that you design that class, I mean, we talked about design patterns. Let's put this on the side. But I mean, the actual code that you do, how do you go about designing a class?
2 episodes ago, I've given the same advice. The first thing you do is keep things simple, as simple as possible. So write the code in such a way that it solves a problem, but no more. But then eventually you'll realize that there may be 2 different ways to do things. 2 different possible implementations. And that's the point where you then start to organize things. So you do not duplicate stuff in order to have 2 completely separate things, and you do not manually change code. Now you introduce a pattern in order to manage the 2 variations of some implementations. And this is the usual way it should be done. You do not start with a pattern in order to just use some pattern. No, you start simple. And then if you come to a point where complexity rises and you want to manage this complexity, then a pattern applies. Allow me just one quote from Venkat Subramanian, because I just love that. So he said, as a developer, you should not get up in the morning and say, well, today I'm going to use a pattern. No. You should write your code and use the pattern as a solution to solve a problem. It's not necessary to use a pattern, just to use it.
The one subject that in the sessions that we had so far, we haven't really touched on is the subject of refactoring.
Oh, yeah.
I mean, there's a whole can of worms in the sense that you can easily spend another hour on talking that about alone. But it just occurred to me that when we talk about, okay, you start simple and then the code grows in complexity and in what it does. And the purpose of the code very often changes too. So reorganizing that is called the refactoring. Is then that the class design is, and along with all the other things like testing, etc., is part of that refactoring process.
So let me just go back to the definition. Refactoring changed the structure of the code, but never the behavior, which is pretty important indeed. When you refactor, you just try to improve the structure. You never add any new code. A new code in the sense of new behavior, new functionality. We talked about test-driven development for a little bit in 2 episodes ago.
Yeah.
The 3rd step in this test-driven development cycle, the 3rd step is just refactoring. So I have my code, I have my tests that make sure this works, but now I can refactor to make this more beautiful, more correct, perhaps in the sense of better to maintain. But I do not add anything, because before I add anything new, I should write a new test. And so refactoring is just structural changes.
Refactoring is indeed not introducing new behavior. What I wanted to say is that software often does change the behavior, in which case it's not refactoring, it's, rewriting.
Something new, Say that there is new behavior and some new implementation. You want to support another graphics library, another database vendor or whatever. Now you realize you have 2. The old one, the new one, you might want to support both. This is now when you can start to introduce a design pattern. Any pattern. Strategy comes to mind, but there may be other solutions too. This is how to now adapt the design of the class. It may still be refactoring because you now change the structure of the class to support multiple implementations. By now, for instance, introducing polymorphism. But adding the new graphics library, database, whatever, that first requires you, strictly speaking, in the TDD sense again, first to write the according test, support that, and then you might refactor the code such that it's easier to support both.
So there's a bit of an art, isn't it, in terms of class design and design patterns?
And you said art. I would call it a science. I mean, it's probably a little bit of both. You can only prove that there is a bug by writing a test that shows that there's a bug. This is kind of the scientific way of doing things. You prove something to be incorrect, a theorem to be incorrect, a program to be incorrect. But it is an artful thing. You also need to know your tools, how to use them properly, when to use them properly. So I think it's a little bit of both. Okay. Which, by the way, may be exactly the reason why AI will not take our jobs so quickly.
I hope not.
The creative part is where AI is very bad at this point.
Well, talking of that, there are elements of AI where it could help, like writing boilerplate code, like test cases, etc.
The repeatable stuff, the boilerplate stuff, this is something that AI can do wonderfully. This helps us because it saves time. But the creative aspect, the artful thing, that's something that the human mind can do so much better.
Yeah, and let's hope it will continue, at least for our own sake. On that very happy note, thank you so much for your time, Klaus.
Yeah, my pleasure.
Well, we did go a bit off route with our chit-chat about AI and coding, although Klaus and I do think that a lot of the fun and reward that you can get out of coding is that it can be creative. Which takes me right back to design patterns. The phrase is now commonly used in programming, and there are quite a few books on that. Klaus mentioned, for instance, The Gang of Four, which is a classic, but it actually started in... Yeah, that's right, building and construction, or to be more precise, architecture. It was an influential book called A Patterned Language, written by one Christopher Alexander, Sarah Ishikawa, and Murray Silverstein from 1977, in which they tried to identify common patterns and a common language for them to build houses or construction in general. Design patterns in programming try to do something very similar. Classify problems and try to find a common way to describe them, and then, as a next step, propose solutions or solution approaches. Sooner or later, you'll stumble on a coding problem and think, surely someone must have done something like this before. And in many cases, that's true. The Gang of Four describe a number of these kind of common problems in their book on design patterns, and conveniently in C++. But theirs is not the only one. Builder, factory, and command patterns may be common these days, but this is the age of very complex and often distributed systems, and the kind of design patterns for that go way beyond that from the Gang of Four. One of the books that I can highlight here is the book and wonderful blog post from Martin Fowler on so-called patterns of enterprise application architecture. I also like to shine a light on Gregory Hopper and his book Enterprise Integration Patterns. Right, you'd be happy to know that we reached the end of this rather dense and long episode. And I hope what Klaus and I talked about made some kind of sense, so do let us know. But as usual, before I leave, let's have some quiz questions. The first question is, there is something called the messaging pattern. I appreciate this may be new to you, but try look it up and see how this could help in applications that are distributed over different components and sometimes systems. And secondly, Klaus and I talked about virtual functions and also pure virtual functions. Are they actually different? And if so, how? Have a think, and for those of you studying at UCL, happy reading week. And because of that, the next episode will be out in 2 weeks' time, and I hope to see you then. Oh, and just one afterthought. The sound samples that you hear from building sites and rings, by the way, are from the wonderful BBC sound effect sites, which is free to use for anyone who's using them for non-commercial purposes. You will find the material for this course on the Moodle platform at UCL. This podcast is produced by Peter Schmidt. The music comes from Daniel Lindenblatt in Berlin, Germany. And finally, thank you for listening, and I hope you enjoy the course. And with that, goodbye.